We've talked about the surface excess of solutes. What about the solvent itself? Let's imagine three different drawings. We can imagine taking our solvent and putting it here, and then putting in our Gibbs dividing surface. And we could put our Gibbs dividing surface up here, like that, well above the surface. And if we do that, then by definition, the volume of the container is this. And we know that the amount of solvent that we can attribute to the surface would be the total amount of solvent minus the solvent that's in the air minus the solvent that is in the liquid state. So we're going to call this down here liquid, and up here is in the air. Okay, so this is the total amount, so we can subtract what's above the line, what's below the line, and if there's any difference between the total and the amount here, then this will either be a positive or a negative number. Well, in this case, we can rewrite this as the amount at the surface of the solvent is the total amount, and for simplicity, let's assume that we have a solvent that's not very volatile, so this will be approximately equal to 0. So what's this going to be equal to? Well, this is just the concentration of the solvent times the volume V. And we can see right away we've plugged in a V that's bigger than the actual volume of the liquid. So this term is going to be bigger than the actual number of moles of solvent. And so that means that the surface excess in this case is going to be a negative number. On the other hand, we could imagine taking our solvent, putting it here. We could put our Gibbs dividing surface down here. And by doing so, we're defining the volume of liquid as being smaller than it actually is. So in this case, N for the solvent, the amount of solvent at the surface, is going to be the total amount minus air minus what's in the liquid phase. And once again, we'll assume this is approximately 0 and rewrite this to say we've got how much we actually know there is of moles of liquid of solvent minus the concentration of solvent times V. So it's exactly like the one we just did, except for here this volume is artificially low, which means this term is artificially small, which means this difference is going to be positive. Basically, we're attributing all this liquid up here to the surface, that surface phase. Over here, this is the deficiency of we're saying there should be this much liquid and there isn't, and that's why it's a deficiency. So the third case, of course, would be to put the Gibbs dividing surface where the physical interface is. So we'll put our Gibbs dividing surface here. And in this case, the surface excess amount is going to be total minus concentration of solvent times V. And V is this volume, the actual volume of the container. So that means if we multiply the volume times the concentration, we get the actual amount. And so these are equal. So in this case, N sigma is equal to 0. And of course, the surface excess of solvent is also going to equal to 0. And this is the most common convention to do in surface science, is to say I'm going to place the Gibbs dividing surface such that the surface excess of solvent is equal to 0. And you can see that's the convention that kind of makes sense. So we're going to be doing this for the rest of the course.